I'm Malikus Said from the School of Computing at Telkom University. Today, I am presenting our research titled Bridging the Plausibility-Validity Gap by Fine-Tuning a Reasoning-Enhanced LLM for Chemical Synthesis and Discovery. I believe this work represents a crucial step in making generative AI a reliable partner for chemists. I note that this is the last presentation before we will have lunch, so I will try to keep this short. Large language models, we have to address the elephant in the room first. Large language models are excellent at generating text that looks scientific. They use the right jargon, the right tone, the right structure. Basically, because of market pressure, LLMs are not designed to look not sure or to look doubtful or to maybe just to say that I don't know the answer. When they don't know the answer, they provide the false answer convincingly. In scientific domains, looking right is not enough. It has to be right. We term this disconnect the plausibility-validity gap. Here's an example of the plausibility-validity gap would look like in chemistry. On the screen, you can see the issue. A large language model confidently generates a reaction mechanism that looks plausible for a non-chemist. Maybe some of you here is also an expert in chemistry and will immediately spot the problems in the large language model's response. For example, a carbon atom that has more than 4 bonds, or a reaction that violates conservation laws, where the reactant must equal the product. The text is plausible, but the chemistry is invalid, even just a first glance by an expert chemist. This is the specific gap that we aim to bridge. This is our related works. This is part of my master's thesis. Initially, I planned to only build a framework to help chemists interface better with a general LLM. So we do a prompt engineering on their input, and then we validate the LLM output, and then we generate reports that are easily understandable by chemists based on that LLM output. This work has already been presented in an earlier conference. But when we are building that software to help chemists interact better with LLM, we found that the performance of the LLM is lacking. It has become a bottleneck in the program itself. So we try to do a fine-tuning, we document the process, and we present the result for the general academic audience. In this research, the paper that we are presenting, we are only using dual domain dataset of 30,000 entries. We are also building a much larger dataset of about 1 million entries because we believe this will help to resolve the remainder about 3% inaccuracy in the language model when combined with the framework that we built. So the framework only has 83% accuracy. The paper that we are discussing today, the framework plus our LLM, is 97% accurate, while we hope that we can solve the remaining 3% inaccuracy by using larger dataset. On our previous work, this is I should talk the earlier talk in this slide. To give you the picture of our previous work, we built a framework to add a guardrail for AI, and then we to try to train or fine tune a better AI in this paper, and then we will try to solve the remaining mistakes and inaccuracy by training the LLM on a larger dataset, and we understand that it might require even larger resource. So the thought process, why do we even bother to fine-tune LLM? Our hypothesis was specific. We believe that combining a model architecture designed for reasoning with rigorous domain-specific fine-tuning would outperform both generalized model and complex tool-augmented systems. We will verify this hypothesis later. Our strategy was twofold. First, we try to pick a reasoning-centric model because the plan is we have to be responsible for the answer we provide. We are not doing total explainable AI yet at this stage, but seeing how the LLM reason offer insight on how they arrive at that answer. Saying that, second, we are trying to create a dual domain dataset that covers both properties and reactions. Using that dataset to fine-tune the LLM efficiently using LoRa. Why do we choose magistral small? First, it is open source. So if it's trained with also open source dataset, we can just publish the resulting model in Hugging Face or website for hosting LLMs. Second, it features a native chain of thought architecture. It explicitly separates its reasoning process in the think block before giving the final answer. So, as I said, this allows us to inspect the logic, not just the result. When we compare this to Mistral 8 billion standard H model, that's also from the same AI company, Mistral AI from France, we see the architectural focus on reasoning actually translates to better chemical accuracy. So regarding the dual domain dataset, we are focusing on two types of knowledge for this LLM fine-tuning. First, descriptive knowledge on how to understand molecular properties. Second is the procedural knowledge, understanding on how reactions occur. We built a dataset of over 30,000 examples in this case, we're training this LLM by combining molecular properties from pharmacopoeias and reaction data from past academic publication. We try to apply rigorous standardization to ensure the dataset is of high quality. I'm also happy to share that as part of data procurement efforts, I said to quash the 3% remaining inaccuracies and mistakes, we have released the property prediction segment of our dataset on Kaggle. This is around over 400,000 validated molecules. As you can see on the dataset, because our rigorous standardization process, there's zero missing value for over 3.2 million cell entries. So 400,000 lines times 8 columns. There is zero missing entries. While the reaction dataset is more restricted due to licensing, we are actively trying to get if we manage to get an open source dataset that we can release or get approval from the proprietary owner of the dataset, we will also try to release that, but we have no firm timeline as of yet. So what's the result? This is training with the 30,000 dataset yet. We have not used the 1 million entry dataset for fine-tuning. So training a 24 billion parameter model, this magistral one, is computationally expensive. To manage this, we use LoRa adaptation. And even when we are using parameter efficient fine-tuning like LoRa, we still need the latest GPU that we can get our hands on. These techniques freeze the pre-trained weights and then inject small trainable metrics like an adaptation layer. This allows us to update only about 0.1% of the parameters while retaining the model's general capabilities. We use 8 NVIDIA B200 GPUs for approximately 2,400 GPU hours. Take note that NVIDIA B200 GPUs is like 2 GPUs in one card. So there's in one DGX B200 server, there's actually 16 GPUs that I can see through Ubuntu. So how's the result? On the left side, we put the baseline Magistral and baseline Ministral that are straight from Mistral AI, and after we fine-tune, even we get better result from fine-tuned Ministral than from the non-fine-tuned Magistral. So actually, fine-tuning give better results than chain of thought process. On the hardest metric, the synthesis feasibility, accuracy triples from 26%, about triple from 26% to 74.4%. So we also observe some interesting thing on the learning hierarchy. Syntax is the easiest one for the language model to learn. Epoch 1 and 2, it already get the syntax correct, while the synthesis planning is the hardest to learn. This actually mirrors my experience during my Bachelor of Science years at my chemistry major. When I take an organic chemistry lesson, the reaction mechanisms and synthesis planning is the hardest to learn because it actually need us to look 2 steps forward. We actually we have a novel approach that we start with the product and then try to work backwards and so on. So this is the computer needs to strategize, not while usually they only work like 1 step and then 1 step and then 1 step as part of the chain of thought process. Our takeaway is synthesis planning is a deep skill, hardest to learn, and it continues improving. Maybe if we have even more time to do fine-tuning, it will continue to improve. But the basic syntax, like how to format smile strings, it very quick to learn. So maybe this might be more of interest if this is a chemistry conference. So I try to keep the case study not detailed. We asked the models to propose a route to create to synthesize helicondrin B fragment. The baseline model, failed. The answer is simply cannot be done in normal laboratory conditions. Even we are not talking industrial conditions. We are even talking on ideal laboratory conditions. We cannot do the reactions that the baseline model proposed. However, the fine-tuned model, after around 60 plus tries, actually managed to find a plausible answer based on our expert assessment. The fine-tuned model proposed a 15-step route on how to synthesize a highly contained B fragment. It explicitly reasoned about stereochemistry, selected, this is the part where it gets creative. It selected a specific brown collaboration to ensure synthesis selectivity. Because the molecule has multiple stereocenters, this reaction is, I feel this is quite sophisticated because it's rare that we need to consider multiple stereocenters when synthesizing a molecule. And it also somehow managed, this is maybe prior knowledge from Mistral's training, yeah. It somehow cited an F1 synthesis of calipeltoside A, a different molecule, but we are using the similar methods that he used to do this transformation using brown collaboration. So, this is based on the request of the reviewers of the paper for this conference. How is our model compared to the state of the art? Compared to the transaction models, we are better, yeah. We have almost 100%, as I said, 97% accuracy. But for total augmented systems, this is we are just using the base LLM model. We don't have an external validation tool that like what the ChemPro use. We have a similar rating from expert when we are giving them blended answer on ChemPro answer and the Mangi cell small. So what the human thinks when we are comparing our model against another Master of Science student in chemistry when trying to solve the same problem. The model is statistically indistinguishable while in reasoning in chemical creativity. While in the reasoning creativity, interestingly, the model actually scores slightly higher than humans because it provides consistent and detailed explanation every time. While humans, when we try to do an intense question and answer session, it falters there because tiredness, bored, and so on. However, in head-to-head preference tests on which answer the experts like better, the humans is still preferred on about 60% of the case. But even 40% preference, I think is a win for a chemistry model. So we have to be honest about our limitation. Stereochemistry still remains a challenge, contributing 1.8% error rate from our 2.9% error. So more than 2/3 of the error is attributed to stereochemistry. Simply because mass are one-dimensional strings and trying to represent 3D space. Maybe we need to use INCI, International Chemistry Identifier, to represent the 3D space. We also face a knowledge cut-off, so we cannot account for novel chemistry processes and products. The model has to basically be continuously trained to account for new methods and products reagents. Naturally, running a 24 billion parameter reasoning model is heavier than standard models. We hope that we can maybe look at hybrid architectures to solve the 3D representation issue, but we have no commitment to pursue this approach as of now because, as I said, this is just a part of the software that we engineer. So, in conclusion, we have successfully transformed a generalist language model into a specialized scientific assistant. We proved that by combining reasoning-centric architecture with domain-specific fine-tuning, we can bridge the plausibility-validity gap. We are moving from AI as a tool to AI as a listening partner. This specialist model, we hope, will serve as the intelligent engine powering our wider valid model framework. Thank you very much for your attention. I have included my contact details here, and I am now happy to take any questions you may have.